Okay, hello and welcome back to Chemistry Talk. Today, we'll be having a discussion of acids and bases, continuing um, on from, the Bronsted-Lowry definition, what acids bases are, and the next thing to talk about is conjugate pairs of acids and bases. Um, so, the term conjugate actually comes from a Latin word conjugare, meaning to join together. You see a lot of conjugates in mathematics, but conjugate is the resulting base or acid from a reaction. So reactions between acids and bases always yield a conjugate base and a conjugate acid. So Bronsted-Lowry said that acids donate protons. So after the acid donates the proton, the result that's going to accept the proton is that acid's conjugate base. After a base accepts a proton, it's now going to become that conjugate acid. So this concept, it really stems from Bronsted-Lowry because Bronsted-Lowry said that the acid donates the proton, the base accepts the proton. Now the resulting two or more compounds or ions, the result of the acids donating of the proton, the conjugate base will accept that proton. And after the base accepts the proton, you get the conjugate acid. Now, there is one thing I do want to point out that's known as amphoteric substances. These are substances that can act as an acid or a base. Very rare, but there are a couple, so I just wanted to bring it up and give you an example. So here we have water as my example. Now I'm mixing water with a strong acid, hydrochloric acid, and I'm getting chlorine ions and hydronium ions as a conjugate base. So water is acting as the base here because it is accepting that proton that it donates. Now here, water is donating the proton. It's losing the proton, and the ammonium is accepting the proton. Therefore, it's acting as the conjugate acid. So water can act as a base or an acid. Okay, so I think I have three examples here on how you determine conjugate base and acid. So the conjugate base of HSO4 minus is what? Okay, well, first thing you want to identify here is that HSO4 minus is a weak acid, which means it came from a strong acid. So HSO4 comes from sulfuric acid, H2SO4. And when you dissociate H2SO4, it's a strong acid, so you don't need the equilibrium. You get HSO4 minus and a hydrogen ion. So that's where HSO4 minus comes from. Now, it's important to understand this because HSO4 is a weak acid. So if you're going to dissociate a weak acid and look for conjugate bases or acid pairs, you need to include the equilibrium. Shows that the reaction can shift back and forth. So when you dissociate HSO4 minus, you're going to lose this hydrogen ion. So you're going to get SO4, and this is going to have a -2 charge now, because it's lost two hydrogens, one in the first step, now in the second step it lost two hydrogens, so it has a -2 charge now, and you're going to have a hydrogen ion. So per Bronsted-Lowry, the conjugate base accepts the proton. So the acid donates the proton, and that's the conjugate base. So here, HSO4 is our acid, and it's donating the proton. The conjugate base of HSO4 is SO4 minus 2. It's losing that proton. So I'll say it again. After the acid donates a proton, the result is the conjugate base. So here, HSO4 is donating a proton into the solution. You're getting the hydrogen ion, and you're left with the conjugate base and the conjugate acid. So HSO4 has lost a proton, and its conjugate base is SO4 minus 2. Okay, what's the conjugate acid of NH3? Well, NH3 is a weak base. So when you're dissociating a weak base, two things you have to keep in mind. You have to include water, and you have to write the equilibrium sign because the reaction can shift back and forth. So when you dissociate the weak base, what you end up getting is ammonium, which accepts the proton, and you get the hydroxide ion. In this case, the conjugate acid of the reaction is the NH4+. After the acid donates the proton, after the base accepts the proton, the resulting is the conjugate acid. And here you have the resulting base. So after the acid donates a proton, you get a conjugate base. So here the water's acting as the acid, it's donating the proton, and you get the conjugate base hydroxide. Here NH3 is acting as the base, it accepts the proton, you get the conjugate acid. So here the conjugate acid of ammonia is NH4+. Okay, identify the Bronsted-Lowry acid, base, conjugate acid, and conjugate base in the following reaction. Okay, so what you want to do first is identify on your reactant side which is your base and which is your acid. So this has a hydrogen attached to it, so I already know that this is my acid. And this is my base. Now what's going to happen? Well, it's dissociating 100%, and I'm getting a resulting solution that has OCl minus, means it lost a hydrogen ion, so it's become the base. And now I have this solution, which has accepted the hydrogen ion that the acid donated, and it's become the conjugate acid. So the conjugate acid-base pair here are these two. The HOCl minus lost the proton, it became the conjugate base. The C6H5NH2 gained the proton, it became the conjugate acid.